Good morning, good afternoon to another Uponor Academy webinar. Thank you again for joining us today. We'll be discussing and presenting on Weholite structural polyethylene design systems for wastewater and stormwater applications. Our presenters today are Brian Maguire and Tripp Waymack from Uponor North America. Just before we begin, a couple house rules. If you do experience any audio loss, simply refresh your browser. You should be good to go from there. Use the chat box located on the right side to send us questions that will be addressed via email. All attendees will receive a 1-hour PDA certificate from Uponor. And lastly, check the resource box for brochures, webinar schedule, previous webinars, or to contact an Uponor sales rep. Now, without further ado, I'm going to pass it off to Brian to get us started.
Good morning, and thank you all for coming here today. My name is Brian Maguire. I'm the North American Project Services Manager for Uponor Infra. Also with me on the phone today is Tripp Waymack. He is our Regional Engineer for the Southeast United States. We'll be covering Weholite structural polyethylene systems and applications for wastewater and stormwater projects. This is a 1-hour technical presentation. A little bit about our agenda here today is we're going to provide a brief introduction to Uponor and Weholite systems and applications. We'll discuss thermoplastic welding, general, quality control, structural design beyond pipe, review buoyancy countermeasures and backfill standards, and then Tripp will cover wastewater and stormwater applications and some project-specific details. For those not familiar with who Uponor is formerly KWH Pipe in North America since 1966. We've also been manufacturing pipe since 1917. We were renamed Uponor Infra in 2013 through corporate acquisition. However, we've been manufacturing Weholite pipe, which is the basis of a lot of the structures you're going to see today since 1983. We're an ISO 9001 certified manufacturer. We have ASTM standards and certification testing for full-scale deflection testing of all diameters we produce, and we'll talk a little bit about that in a minute. And we have 2 manufacturing plants in North America. For those not familiar with Weholite, ASTM F894 defines structural profile wall polyethylene. Uponor is able to produce this material in diameters of up to 132 inches. It utilizes a robust rectangular cross-section, as you can see there on the right-hand side, with an ID and OD weld to create a robust high load carrying capacity system capable of being fabricated and designed into a wide array of applications. Here you can see that rectangular cross-section as it is extruded from the line, and the ID and OD weld that are used in pipe to create a mandrel wound, helically wound configuration, and in panel to create flat panels of material called Wehopanel. You can see the profile being extruded and wound, and our quality control inspection team inspecting the pipe. This material should not be confused with standard solid wall or corrugated exterior smooth interior M294 polyethylene pipe. Because we can accommodate much higher fill height capacities and larger diameters in that material, it's a much more robust material. It shouldn't be confused with lighter weight material such as M294. Here you can see structural panel called Wehopanel. It's useful for the production of buoyancy countermeasure bases, tops of structures, internal baffle walls, and rectangular structures of a wide array of configurations. The 2 materials, Weholite and Wehopanel, are combined through thermoplastic fusion welding and fabrication to create a host of applications and project-specific designs. With respect to this presentation today, we're focused on stormwater detention, CSO storage, pump stations, vertical applications, and wastewater treatment structures. All of these applications offer a 100% polyethylene system with a 100-year design life and infinitely configurable to meet the project-specific needs. These next few photos simply demonstrate a wide array of systems that we can produce. Here you can see different diameter header system. On the right-hand side, you have an infiltration retention type of system. Here's a number of manhole structures, horizontal, vertical bends, and manifold systems that can be produced. Expanding these photos to some larger photos with a little bit more detail. Uponor has traditionally been known for producing large diameter, high quality pipe for low pressure applications for pipeline projects, penstock, irrigation, CSO, and interceptor sewer projects. Here you can see an example of one of those projects you may be familiar with us, with a manhole riser off the top of structure being field welded. But beyond pipe, we can combine Wehopanel and Weholite modular and Weholite to create a wide array of systems. So you can see a manhole structure with a complex inlet and outlet control, as well as a Wehopanel vertical wastewater treatment structure. This is another example of combining Wehopanel and Weholite to meet the needs of the project. This is an above ground UV treatment system at a potable water treatment facility. This system utilizes Wehopanel to support the cradles and haunches, and Weholite for the horizontal vessel. Another above ground application that uses Wehopanel to support the system in an unconfined or unconstrained application. And there you can also see the Wehopanel reinforced bulkhead and flanged coupling for field connection. Manholes can be developed for an infinite array of applications up to 132 inches and about 50 feet in depth, similar to pump stations. We can also produce pump stations with all the internal components, piping, fittings, breakaway fittings, guide rails, all pre-manufactured and installed and ready to be backfilled and plumbed in the field. This significantly reduces the installation time of these structures. It also provides a level of quality control, given that we can test the system and make sure it's leak-free prior to it leaving our production facility, which we'll talk about here in a second. But this is a great example of the versatility of Weholite and Wehopanel to meet the needs of a project, while providing a 100-year design life in a system that's immune to hydrogen sulfide deterioration, pH, corrosion, and abrasion. The versatility of polyethylene allows us to fabricate manholes, junctions, and bends much more cost effectively and frequently eliminate structures in comparison to conventional concrete techniques. You can see we're able to creatively solve for this junction structure using polyethylene and Weholite. However, alternatively, if this were cast-in-place concrete, this would be an extremely large body, maybe 15, 20 feet wide, with a large riser structure on top. So we're able to accommodate geometries and structures more cost-effectively with polyethylene, while still providing that enhanced durability and rapid installation time in the field. We showed you a little bit about pump stations. This is a nice pump station project. Tripp will get in a little bit more detail on. This is a 132-inch by 30-foot tall pump station, quadplex submersible wet well. The breakaway fittings were anchored into cast-in-place rebar reinforced concrete to support vibratory load. And the buoyancy base, as you can see there, is Wehopanel with steel reinforcement in it. This structure was able to be delivered to the job, set in the field, and backfilled and plumbed within 1 day of delivery. So speed of installation in addition to enhanced durability. Here's a simple vessel relatively, but it shows our capabilities using the Wehopanel bulkhead to reinforce the ends and provide inlet and outlet controls in a simple 100% polyethylene vessel. Here's a little bit more complex vessel, singular vessel, but on this one, this is a wastewater project that Tripp will discuss in a minute that uses a MBBR, moving bed biological reactor treatment process inside, and as such, there are multiple chambers and sections in the structure and pumping and piping between them, requiring complex fabrication, reinforcement, and details within the structure that we can achieve with Wehopanel and Weholite. So we've shown you some smaller structures. On the larger scale, we do large volumes of storage, especially when the need for a watertight, robust system is evident for the project that requires large volumes of storage. We can produce large diameter manifold systems such as this, and we can even do this in a double tier, double stack configuration for large volumes of storage. We can do same diameter manifolds, or as you saw earlier, variable diameter manifold systems. When site footprint is limited and large volumes of storage are required, we can often get additional volume of storage between the pipes using the same diameter manifold configuration you see here. If you have available site and don't need that additional storage, usually bulkheads and small diameter manifold connections, hydraulic connections between the bulkheads is usually more cost effective, but it's very project specific and dependent upon the available footprint and volume of storage for the job. Again, even though we're going large diameter structures and large volumes of storage, we can still provide the intricate level of fabrication and detail necessary for the job. As you can see here, we have invert channelization to support access and maintenance of the CSO header system. Here you can see, just to demonstrate the scope and size of that particular system, one of our manufacturing crews standing inside the pipe, demonstrating the size of the system. As we said earlier, we can accommodate directional changes, horizontal, vertical bends, manhole structures, but this slide reinforces the fact that we can do that in diameters up to 132 inches, and this shows some fabricated bends using 132-inch Weholite to eliminate manhole risers and junction structures and directional changes. It's just an advantage of Weholite. And before we get into the more technical aspects of the project, of the presentation today, let's talk a little bit about Weholite modular. Weholite modular, Wehopanel rectangular structures here in North America can be developed for any above ground application for wastewater treatment or storage. We also will soon have the ability to bring these systems below ground. We've actually run full-scale live load tests and developed strain gauge and pressure data around the system to determine its performance in a buried application. So we'll be bringing that to the market space here in the near future. Currently, Weholite modular is used for above ground applications for wastewater treatment and storage. As you can see here is a 14-foot tall, 12-foot wide, roughly 40 feet long prefabricated wastewater treatment. This is a TSS particle settling and pre-treatment structure that has internal baffle walls, controls, and hopper bottoms to remove larges and settleable solids. We can also do outlet control structures for stormwater ponds or inlet control structures as well. And these particular structures have internal weirs and orifice control to regulate flow under gravity head. So before we can really grasp or understand how we combine Weholite and Wehopanel to create such a wide array of structures, it's important for us to have a baseline understanding of thermoplastic fusion and extrusion welding. Extrusion welding should not be confused with techniques such as gluing, brazing, or soldering, which do not melt the base material and actually result in a seam or a weak point in the base materials that are joined. Conversely, extrusion welding endeavors to heat the base materials and the filler to a prescribed temperature to create a weld pool where we can get some homogeneous weld pool and molecular alignment across the seam. And given that we have a thicker cross-section at the weld than the original base material, we would expect by design that that weld would be the strongest part of the system. And as we'll show you in deflection testing and destructive testing, the weld is the strongest part of the material, and we confirm that through quality control. For those not familiar with extrusion welding, it's a quite simple process where we feed a polyethylene feed through granulate funnel or wire reel through an extrusion chamber, which heats the material and creates a molten mass that's applied to the substrate base materials through a welding shoe that's designed specifically for the weld in question. We also simultaneously apply air by heating it through a chamber and applying that hot air to the base materials to bring them to the prescribed temperature. So extrusion welding heats the extrusion material and the base materials to the prescribed temperature to create that homogeneous weld pool across the section. Here you can see an operator working in a Wagner extrusion gun, heating a polyethylene vertical riser and a HDPE base. You can see the dull appearing haze that follows that weld is a quality weld, and the thick molten mass of material that's bonding those two materials together. There are two standards applicable to thermoplastic extrusion welding. The older standard, DVS, it's been around for some time. It provides not only quality assurance and welding training and guidelines for operators, but it also provides design calculations and structural conditions for different welds and their strengths. Uponor relies heavily upon DVS guidance for development and structural design of its systems. There's also AWS B2.4 that's a developing standard specifications, rather self-regulated at this point, but it is a standard we may encounter in the United States and in Canada related to thermoplastic welding here. There are a number of ASTM standards and specifications applicable to extrusion and thermoplastic welding. We're not going to read the laundry list here, but we will point out some of the important ones. ASTM F1759 is applicable for all vertical applications, so manholes, manhole risers, even manhole risers off horizontal vessels would have to be developed and designed in accordance with 1759. Another important standard is ASTM D2321, which governs the backfill and installation of the systems. We'll talk about that in a little bit. And then lastly, ASTM F894 is the applicable standard for Weholite profile, structural profile wall pipe. Quality assurance testing as it relates to extrusion welding to make sure our systems do not leak. The first line of defense is visual inspection. We referred earlier to the photo where we said it had a heat-affected zone or haze. We want to look for a dull-appearing haze to follow the weld. Overheated or poorly welded polyethylene will have splashes or shiny splashes or discontinuities in the weld that would lead us to remove the weld material, regrind the area, and re-weld it. So visual inspection, much like steel welding, is your first line of defense for quality control. The second line of defense that we at Uponor employ, which is unique to Weholite and Uponor, is the fact that we're able to pressure test all of our fabricated elements prior to them shipping to the job site. The annular space inside the Weholite vessel, because it's continuous, when we discontinue that space through penetration or any fabricated element, we're able to pressurize across that discontinuity to ensure that the weld there holds pressure, and we'll show you a photo of how that's done. And the last line of defense is infield leak detection testing. That's either infiltration or exfiltration testing. Exfil is typically a 24-hour drawdown where they'll fill the structure with water and then observe drawdown time over a 24-hour period of time. Infiltration testing is they'll leave the structure empty under groundwater pressure from the exterior of the structure and observe how much water gets into the structure. But obviously, if the first time you're finding out your structure has a leak or there are issues, potential issues with your weld is in field, it's usually extremely difficult to fix that in the field. We want to know about it before the structure is delivered to the project and backfilled, which is why that pressure test of internal voids across all the angular spaces and fabricated elements before a system leaves the plant is critical to ensure a leak-free system is delivered to the project. Here's a snapshot of the system pressure test. We drill a hole in the system at any point of discontinuity, whether it's the end section, pipe penetration, bulkhead. We can drill a hole in the adjacent profile, pressurize that. And if it holds pressure, we know that that the weld adjacent to that penetration in angular space is leak-free. We also perform full-scale deflection testing, again, on all RSCs and diameters of Weholite that we produce, as well as our solid wall Sclairpipe. And we're one of the only manufacturers in North America that produces, that does full-scale deflection testing on all the materials we produce. And as we talked about earlier, we do destructive testing in the form of tensile strength testing for our systems. If you look at the section on the top left-hand corner of your screen, you'll see a coupon sample is cut from 3 profiles of pipe where we have 1, 2 welds. Transferring over to the photo in the middle, you can see the weld at the top and the weld at the bottom, and the profile section of pipe between the two. And we apply a 2900 PSI tensile force to that particular sample, and as expected and by design, we want the profile to fail and not the weld, because the weld is the strongest part of the material. We would expect that the profile would fail, and that is the case here in this particular example, and as part of our quality control and standard operating procedures under ISO. Here you can see coupon samples that are usually shared with the client to demonstrate that the material they have has high quality welds exceeding design tolerances. So just to transition here into structural design beyond pipe, we should talk a little bit about pipe design. And pipe design applies to any Weholite pipe that's in a horizontal configuration under fill. When we exceed that parameter and we go to baffle walls, bulkheads, or high cover or low cover applications, we're beyond standard pipe design. But we should understand what pipe design is. And Weholite ASTM F894 polyethylene structural profile wall pipe is designed in accordance with Chapter 6 of PPI. You can see it there, and there's the link up top if you're interested in downloading that. The design is basically based on Spangler's modified Iowa formula. You can see there in the top right for deflection. We can also calculate buckling, vacuum load, and other forms of loading on the pipe in accordance with PPI Chapter 6. Weholite F894 pipe utilizes a ring stiffness constant, which is different than a ring stiffness. Ring stiffness constant has been developed specifically for F894 pipe to address handling stiffness as well, and the need for a stiffer pipe in larger diameters to handle handling and installation in the field. In lieu of becoming experts on Spangler's formula or Chapter 6 of PPI, Uponor has developed an online calculator for horizontal pipe calculations. There are a number of other modules in here for Sclairpipe and Weholite as well, but where horizontal vessel design is concerned, we'd be looking at the Weholite buried pipe design calculation tool here. And this is a free tool to use for any engineers that want to go in there and play around with it or develop their own specification and standard for their own projects. Alternatively, you can call us and we'd be happy to run the calculation for you. But buried pipe design is limited to horizontal pipe between structures or continuous systems. When we get into complex fabricated elements, we're removing large sections of material, we're putting bulkheads and baffle walls. We need to go beyond buried pipe design because it's no longer applicable. So bulkheads, internal baffle walls, risers, penetrations, rectangular structures, all need to have some design calculations associated with them to validate that they're not the weak link in the system. Specifically here at Uponor, we run two types of FEA analysis. The first type is a 2D planar analysis called CANDE, stands for Culvert Analysis and Design. And that enables us to determine the loading of the structure more accurately based on the nonlinear elastic nature of soil. We also use a CANDE 3D FEA analysis for bulkheads, internal weirs, and other types of structures to determine the deflection and the reinforcement necessary in that particular element. And I'll show you both of these. So a CANDE analysis is a 2D slice through the structure. The zone in red is your existing subgrade material. It allows us to model the structure in the backfill envelope for the particular project. This is useful from time to time when we have unusual projects like the photo on the bottom right, which is a double stack system. We'd want to analyze that in CANDE. Or with shallow cover application or deep burial application, we'd want to analyze with CANDE. Essentially, it allows us to build up the structural element in the model the subgrade, model the non-select backfill zone and the critical backfill zone, and then apply our vehicular loading or live loading over top of the structure to determine deflection. So this is an important tool when the ability of PPI Chapter 6 and Spangler's formula to actively or correctly model the structure is limited. We would go to a CANDE FEA analysis to confirm deflection and performance of the system. Similarly, for bulkheads and other elements that require reinforcement or steel to be placed in the angular profile to support the loading, we run an ANSYS FEA analysis to determine deflection, apply reinforcement, rerun it until our deflection is within allowable tolerances, typically 3% or so. So two other items on the rather dry technical elements of this presentation are buoyancy, countermeasure, and backfill standards. Buoyancy is a question that comes up frequently with regards to structural polyethylene systems and buried tankage design in general, whether it's structural polyethylene or other. We have to deal with the fact that Archimedes' principle is very real, and many of these structures are shallow cover applications, don't have a tremendous amount of soil over top of the structure. But essentially, for both horizontal and vertical applications, we rely upon the soil load primarily to counteract buoyancy. For vertical applications, we expand the horizontal footprint of the base plate under the soil column to counteract the buoyant force. For horizontal applications, we create an anchor system that increases the surface area under the soil column. Soil weighs down those anchors and then counteracts buoyancy through the strap system. The weight of the vessel, the weight of concrete, the weight in general provides a very small contributing force downward to the overall buoyant force countermeasure. Typically 5% of the downward force is due to the weight. The other 95% is due to the soil column's load distributed on whatever horizontal projection we can create. So for vertical vessels, we expand the footprint. And for horizontal vessels, we want to expand the footprint as well to capture more soil under the structure. Just for those that don't know, buoyancy is based upon Archimedes' principle. The volume displaced times the specific weight of the fluid. Generally, for buoyancy, we're referring to a specific weight of water. However, for systems that are backfilled with a flowable fill or other type of liquefied concrete mixture, we would have to account for the specific weight of that fluid. But in general, we're talking about 62.4 pounds per cubic foot of water times the volume of body displaced. The force downwards, again, is the force of soil on the projection. Sometimes we cannot ship a projection for vertical vessels wide enough to counteract buoyancy. This typically comes up with very shallow structures. And in that case, we can actually design a cast-in-place collar around the bottom, typically 12 inches thick, number 4 or 5 rebar at 6 inches on center, to increase the horizontal projection. Now, the weight does contribute to the downward force, but a very small percentage of the weight is actually of the net vertical force downwards is due to the weight. And as you can see here, soil column on the base plate force down is 42,000 pounds, and the weight of the vessel is 3,800. So we can see that very little weight contributes to the buoyancy factor. As a sidebar, we'd like to mention this is typically we're not able to get accurate water table information from Geotech or others, or information that we're comfortable as an absolute design. So we'll typically assume water table at grade. Given that's conservative, it also ensures that even if we get that, the structure will not flow. So most of our designs, in lieu of having somebody tell us what the water table information is, will account for saturated soil to grade and water table at grade as a standard, unless someone can tell us otherwise. Sometimes contractor is not interested in sourcing strap and anchor system or doing cast in place or precast. We can provide wheel anchors, which is essentially the same concept. The cross section of that tube is the cross sectional area under the horizontal that provides the horizontal projection under the vertical soil load, and the cross section of that tube is what counteracts the vertical force up with the soil column above it. The advantage of this system is it's completely prefabricated. It sets next to the structure, and all the contractor has to do is pour concrete into the tube that already has steel reinforcing and all the hardware attached to it. So it eliminates a lot of the guesswork for the contractor and gives them a turnkey system to counteract buoyancy. We provide this on projects when needed. And last thing I have before I hand it off to Tripp is backfill standards. Backfill is an important thing. Poorly backfilled structures can have differential deflection. They can have undue loadings applied, and they can pop and leak. So we want to make sure that any structure that's buried in the ground is backfilled correctly with high quality material compacted to the proper level of compaction specified. The standard that applies to backfill is ASTM D2321. That is the governing standard that we utilize in all of our buried structures. Without getting into details of 2321, it's important to understand the critical components of it. We have a backfill zone A, which is referred to as our CBZ, or critical backfill zone. That's where we have a high quality class 1 or class 2 material compacted to 90 or 95%, depending on the project. Backfill zone B is our non-select zone. It still needs to be good structural fill, suitable for roadway fill, and it also needs to be compacted to the same level of compaction of zone A. So zone A and B are compacted to equivalent levels of compaction, and then you have your area in white around, which is your subgrade soil. And that also has to adhere to ASTM 2321 specification. Boiling this down a little bit further, we can see class 1 and class 2 for 2321, where we have class 1 is a crushed rock, angular type of stone. Some may think of this as a 27A or 57 stone or crusher run. Class 2 is a clean grade, coarse aggregate, sandy, gravelly soil. And this also, you may know this as an AASHTO A1 or A3 material. So these are high quality, typically import fill materials that go immediately around the structure, D over 2 approximately, outside the diameter of the system. However, we can, through running CANDE and other means, reduce the spacing between pipes Typically, the smallest we want to see it is 3 feet, and that's just enough to get a walk-behind vibratory plate compactor into the system to ensure we get adequate compaction and passes with the compactor. So Zone A, critical backfill zone, Class 1, Class 2, those are the materials that are necessary around the structure. Now, we can look at, for larger projects, we can look at using other material, especially on extremely large CSO storage projects or other types of projects where import is cost prohibitive. We can look at using locally available materials. The way we do that is we say, okay, you have a local stockpile of material available, share that gradation with us, and then we'll take a look at the system's performance using that material. And quite often it is okay, or sometimes we have to take other steps, additional level of compaction or soil improvement to use that existing material, but it is a possibility if import is cost prohibitive. And last, we have Zone B as defined, is a little bit more forgiving. As we said, it's structural road fill. So with that, I will hand it off to Mr. Waymack to talk about some interesting applications of these capabilities.
Okay, thank you, Brian, and thanks again for everybody attending today. Let me get my part of the presentation up. Okay, so I can't possibly talk to you today about every way that you could apply this to your project, so this is not meant in any way to be an all-inclusive list, but really just to get you thinking about how this material might bring value to your projects. The first thing I'll talk to you about is quantity management and storage volume, because it really is useful in most applications, whether that's stormwater detention or retention, CSO projects, rainwater harvest or rainwater cisterns, water and wastewater treatment, and industrial applications. Even treatment applications require some amount of equalization volume or attenuation depending on the turn down capabilities of your process. But here's a good example of a round storage system, and I want to start with this because it is our most common way of addressing storage, because it is the most cost-effective way to give you volume. So this particular application, you can see, has a lot of different. It's a strange shape because it had varying depths of bedrock, and so we were in an odd site available footprint. So we're able to use different diameters of Weholite and have them shipped, and most of these in 2 sections and field welded to accommodate a really strange configuration on that site. So the next few pictures that I will show you are just going to give you a little more detail of the different aspects of these round systems. This picture shows a 3-barrel system that's hydraulically connected. They're separate vessels. They were shipped in 2 pieces and field welded, but they have separate bulkheads and they're connected hydraulically by piping. It also shows you manway access through risers, also made of Weholite. This is a good detail of a bulkhead. Bulkhead designs vary depending upon the application. That varies depending on the diameter of the Weholite, the buried depth, and we will do finite element analysis to make sure that enough reinforcement is added to keep the deflection very low. This is a very large system, 120-inch diameter. There's actually 9 sections to each barrel, 6 barrels total, and this is a common manifold at the end of each one with a manway for each barrel on each end. Is a close-up of that manifold showing the different pieces on a fabrication level of detail and the manway access. There's a good fabrication drawing to show you that on these manways we can provide ladders, connect them at the bottom, and it also shows a bulkhead, a little more detail on the reinforced bulkhead. And here's another picture that shows you an internal baffle and some internal components to this system. I want to talk to you next about vertical tanks, vertical structures, because they are probably the second most common structure that we do. these are also very, very useful in most of these applications, things like pump stations, structures for distribution, control structures, manholes, receiving manholes, headwork structures. We've designed structures to contain bar screens for headworks, also a very good application for HDPE. As Brian mentioned, the material is available in up to 11-foot diameter, and we can ship these things as long as 50 feet and bury them 50 feet deep into the ground. So quite a large structure. And here's some more detail on some of the internal components and some of the Wehopanel involved in some of these structures. The structures on the left are actually a simplex pump station. Structure on the right was a duplex station without the discharge elbow shown, I believe. And you'll see the Wehopanel top with sleeves. This structure on the right actually had a concrete slab poured on top of it. There's some more detail on that structure on the far right. You can see the concrete slab at the top. You can see the hopper bottoms. Do notice that hopper bottom. This is where we bring a lot of value to these types of projects, because in the field this would be grouted by hand. We can do this in a controlled environment in our fabrication facility. In the center of this drawing, I'll show you a little bit of detail on the concrete slab in the bottom. And pump stations, we incorporate a reinforced concrete slab to absorb the vibratory loads of the pumps per AWWA standards. This photo shows a blown up view of the top of the structure made of Wehopanel. You'll see steel reinforcement in that top. Again, this was going to have a concrete slab poured over it. So what you see in section CC here is a sleeve where the discharge piping would pass through. We'd provide a link seal. That way there's no additional formwork on the top of the structure. The concrete is poured right up to the sleeves and to the sleeve for the access hatch. And this is a good blow up of the concrete, the reinforced concrete slab in the base. You'll see that the discharge elbow anchors are embedded in that concrete. Here's another good picture showing that in fabrication. So I incorporated this drawing into the presentation because it's a very large structure, 10-foot diameter, and I believe almost 30 feet deep. And it has an internal baffle that extends almost the entire depth of the structure, and two ladders to go down inside of it. So hopefully you'll recognize in this type of structure that this could lend itself to treatment applications, whether you have two different environments, an anoxic and an oxic environment, or an aerobic environment. You can do a lot of things with a structure of this size and that amount of volume. Here's a good picture showing one in the field. I believe this was for landfill leachate. There's another fantastic application where HDPE provides value to the client. So the next thing I'll talk to you about is water quality and treatment. Some of the most common treatment in the world: sand filters, hydrodynamic separation, water and wastewater treatment, and industrial treatment. And the picture to the right is something Brian showed you earlier. This is a wastewater treatment, a packaged wastewater treatment system for the Denver Metro water treatment plant. I'll give you more detail on that later. So for water treatment, you'll see some repetition from water to wastewater treatment, but this is just a short list to show you, to get you thinking about some other processes that you might be familiar with, or even proprietary processes that we might not be aware of where this could be applied. Ballast flocculation processes that use sand or diffused air, dissolved air, chemical contact tankage. You can put mixers, submersible mixers, or we could even, we have ways of incorporating top-mounted mixers. We have membranes where you're going to need chemicals to backwash the membranes and clean the membrane. Citric acid, hypochlorite, and sulfuric acid. Those are all very harsh environments where, again, HDPE is the best fit and will not be affected by those harsh environments. We can do clarifiers, small clarifiers with hopper bottoms. Disinfection is not affected by chlorine. It is not affected by UV. The black HDPE that you see has 2% carbon added to it, so it can be exposed to UV and not be affected by it. I mentioned sand filters earlier. I'll show you a couple pictures of some sand filter designs that we did using Wehopanel and Weholite. Storage applies to water. Brian did mention this is NSF approved. And then, of course, you have intake piping and yard piping. So for wastewater, I mentioned equalization and attenuation. Headworks is a fantastic application for HDPE because of its resistance to hydrogen sulfide gas. You can incorporate HDPE into the design of your for your screens, and then your biological processes. Any type of process you can think of. I can't list all the proprietary processes out there, but things like extended aeration, MBBR, membrane bioreactors, and sequential batch reactors are all options where this tank could be applied depending on the size of your treatment facility. Clarifiers, small clarifiers, sludge holding and pumping, disinfection, like I mentioned for water treatment, also applies here. Chlorine contact basins and UV contact chambers are really ideal applications for this. And then intakes and outfalls and yard piping are also applicable here. So I wanted to take a minute to talk to you about this Denver water packaged wastewater treatment system. The Denver Metro Water Treatment Facility is a very large facility being built right now, and they decided that it would be more cost effective to treat their wastewater on site than to pump it. And so in cooperation with Aquanova Engineering, we were able to fabricate this system. It has every stage of the wastewater treatment process, and starting from left to right, I'll tell you what these different environments are. There are 8 total chambers here, and starting with this pipe coming in, that is where the influent first meets the system. It comes into a vertical trash tank where you have an aerated bar screen to remove bulk solids. The tank is within an equalization volume tank, and then you have a 3-stage MBBR tank. The vertical screens inside these chambers are actually a media retention screens. Following that, you have a 2-stage clarifier. And then the final tank is effluent pumping. And within these tanks, you'll see small platforms for pumps. We're not providing the pumps for this system, but we did incorporate these platforms. The pumps would be removed using lifting chains instead of guide rails here, so you won't see any guide rails. These pieces in the bottom of the MBBR chambers are for diffusers. We can install equipment for you. We prefer not to purchase things. We like to keep our scope to the HDPE and the HDPE fabrication. But in this case, the contractor was willing to install those diffusers in the field, but we went on ahead and provided them some support so that he had something to attach the diffusers to. So that's about it here on this one. I will also mention that there was a concrete slab poured over this entire system to accommodate vehicular loading. I'll also show you this quick above ground round tankage that is less common, but it is an option. So that entire Denver water system could have been done above ground with haunch support. So less common, because it is a little more expensive, is Weholite modular or rectangular storage. You saw this example earlier. And I'll show you a couple of drawings of different applications where we've utilized that. I mentioned the sand filters earlier. This is a drawing of what our sand filter would look like using Weholite or Wehopanel, and here's another view of that. And these sizes, obviously, this can be custom made. We're not limited by molds or anything like that. This can be custom made to your individual application, so we can really be efficient in our designs. And here's a couple more drawings. Note the drawing on the far right, where you see handrails and guide rails to allow access to the top of the system. That is a packaged water treatment system there. So here's another system that included to show you some of the, I guess, the sophistication of our fabrication abilities at Uponor. You see the hopper bottom, and I'll mention again, those types of systems are where we can really be cost effective, because it would take a lot longer to do that in the field, but we can provide a very complex structure and do that in our controlled environment. Here's another view of that system. And so from here, the last thing I'm going to show you is just a few photographs and drawings of some example projects that we've done. If you have an application that you're curious to find out if we have done something similar, please contact Faze, and I will provide his email at the end here. This picture you saw earlier. This was a CSO project. Again, this really speaks to the level of complexity that we can achieve with your storage volume on site. Different manifold options, different size options, up to 11-foot diameter, and again, these sections can be shipped separately and field welded. A couple more pictures of that going into the ground, and on the right you'll see the reinforced bulkheads. This LA Federal Courthouse rainwater harvest cistern, this is a project in downtown LA, right next to the Los Angeles Federal Courthouse. It was right next to the building foundation in the zone of influence, and right next to a major roadway, right beyond the orange cones. That's where the roadway or the sidewalk actually began. But this is a 150-foot long, 11-foot diameter cistern, shipped in 3 sections, field welded, and tested in the field with an exfiltration test. This drawing from that project shows that we incorporated a small vertical pump station. This allows us to take full advantage of all of the available volume in a horizontal vessel, and we don't have to account for pump submergence. There's also an internal baffle inside of that. Here's another blow up of that small pump station within that structure. So next I'll tell you, we do a lot of manholes, especially projects where there are harsh chemicals, landfill leachate, and in this case, the Denver airport. They had hydrogen sulfide and glycol that were causing rapid deterioration of concrete structures, so they decided to go with a permanent solution, and we did 16 manholes for the Denver airport, and at a very substantial depth of 35 feet. An excellent project for us and a perfect example of how to use a good application for HDPE. It's another stormwater detention in Ontario, a large diameter structure, 350,000 gallons, a single barrel system, again, shipped in sections and field welded. This is a custom vessel above ground. I think Brian showed you a quick picture of this where it shows the haunch support, but it really allowed the customer to take advantage of an odd footprint that they had available and put in a permanent solution, for a UV system. And this drainage project in British Columbia, in the lower right-hand corner, shows a structure that a complex structure that is easily done in our fabrication facility and not done in the field to save a lot of time and have precise fabrication in a controlled environment. This is City of Fort St. John. You have dissimilar material connections here. We can provide details for all that. If you have any questions about that, please let Faze know. We don't have enough time to cover all of that in this presentation, but dissimilar materials is not a big challenge for us. Please let us know. And here's an example of that right here, how we would transition to concrete. Last thing I'll show you is the West Branch Pump Station in Montgomery, Pennsylvania. This is a very large pump station, 11-foot diameter, 30-foot deep, quadplex submersible pump station that's had a concrete slab over top of it. And I have some great photos from the installation there. You'll see notice the Whale panel base, and here is the reinforced concrete slab in that base to absorb the vibratory loads of the pumps. This picture shows during the fabrication process, but it's a good photo showing the sleeves in the top that, again, prevent the contractor from having to do any form work and pouring that concrete slab. And here's another good picture showing our technicians working on the base, embedding those anchor bolts into the base. And last but not least, a snowy picture of when this thing showed up on the truck. So thank you very much for attending, and please submit your questions to Faye Tariq at the email below, and also submit your sign-in sheet to get your PDH credits. Thank you very much.